Welcome to an introduction to C pointers. Pointers are variables that store memory addresses of other variables. This allows for direct memory manipulation and efficient data handling in your programs. Consider them as a way to refer to the location of a variable in your computer's memory, rather than the value stored there. Now let's discuss how to declare and initialize pointers. A pointer is declared using the asterisk symbol. This symbol is placed between the data type and the variable name. For example, an asterisk pointer declares a pointer that can store the address of an integer variable. The ampersand operator returns the memory address of a variable. To initialize a pointer, you assign it the address of a variable using the ampersand operator. Let's look at the code. First, an integer variable number is declared and initialized with the value 42. Then an integer pointer variable PTR is declared. After this, the address of the number variable is assigned to the PTR variable. Now, PTR holds the address of number. Finally, to access the value stored at the memory address held by a pointer, you use the asterisk symbol again. This is called dereferencing. So, int value is equal to asterisk PTR will assign the value 42, which is the value stored at the address held by PTR, to the value variable. Let us visualize how pointers work in memory. Consider a variable named number, stored at a specific memory address, let's say 0x7FFF5FBFF8C0, and it holds the value 42. A pointer named PTR is stored at another memory address, let's say 0x7FFF5FBFF8C8. Instead of holding a regular value, PTR holds the memory address of number, which is 0x7FFF5FBFF8C0. The pointer PTR stores the memory address of number. When we dereference PTR using asterisk PTR, we are actually accessing the value stored at the memory address it points to, which is 42. Let's explore the common operations you can perform with pointers. First, declaration. An example is int asterisk PTR, which declares a pointer to an integer. Second, assignment. For example, PTR is equal to ampersand variable, which assigns the address of variable to PTR. Third, dereferencing. Using asterisk PTR allows you to access the value stored at the memory address pointed to by PTR. Fourth, pointer arithmetic. Adding 1 to a pointer such as PTR plus 1 moves the pointer to the next element in memory. Fifth, null pointer. Setting a pointer to null, as in PTR is equal to null, indicates that the pointer does not currently point to any valid memory location. Let us go through the example code. An integer variable x is initialized with the value 10. Then, an integer pointer PTR is declared and initialized with the address of x. When asterisk PTR is assigned the value 20, the value of x is modified to 20 through the pointer. Then PTR is assigned the address of the integer variable y. Finally, PTR is assigned null for safety. Pointers are used extensively in C programming. Let's explore some common use cases. First, pass by reference. Pointers allow functions to modify variables from the calling scope directly. Here is the code snippet to swap two numbers using pointers. Second, dynamic memory allocation. Pointers are essential for managing memory allocated at runtime using functions like malloc, calloc, and free. Here is the code snippet for memory allocation. Third, data structures. Pointers are fundamental in creating linked data structures such as linked lists, trees, and graphs. Here is the code snippet for the node structure. Fourth, array manipulation. Pointers provide efficient ways to traverse and manipulate arrays, as arrays decay to pointers when passed to functions. Here is the code snippet to process arrays. To use pointers effectively and safely, it's important to follow best practices and avoid common pitfalls. Let's begin with the best practices. Always initialize pointers before using them. If you don't have a valid address to assign, initialize them to null. Always check if a pointer is null before dereferencing it to avoid segmentation faults. Free dynamically allocated memory when you're done with it to prevent memory leaks. Use const for pointers that should not modify the data they point to. Let us look at the good practice example. Now let's look at some common pitfalls to avoid. Avoid dereferencing null or uninitialized pointers, as this leads to undefined behavior. Avoid dangling pointers, which are pointers that point to memory that has already been freed. Prevent memory leaks by always freeing dynamically allocated memory when it's no longer needed. Be careful to avoid buffer overflows by ensuring you don't access memory beyond the bounds of an array. Let us look at the code to understand the common mistakes. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.